Okay, welcome back. Okay, so I guess, like, at least as a programmer here, this is how I am now going to imagine the machine learning problems. And maybe it's possible over here. Like, I can imagine this one. If I have RGB color values, okay, I have enough of an experience with them, right? Like, if the amount of red is quite high and the amount of green and blue is quite low, return red. If the amount of red is high and the amount of green is medium, the amount of blue is low, return orange. Like, this one I could almost write. It's not a fun afternoon, but it could be done. Maybe I'm not going to think of this as an if statement. Maybe I'm going to think of it as a decision tree, which is the title of the slide. But I think in my mind, conceptually, they're the same, right? Like, what is a nested if-else structure if not a bunch of chained decisions? It's exactly what a decision tree is in my mind, too. So I have some number of features. I have the 30 things in the breast cancer data set, or I have the 64 pixels in the handwritten thing, or I have the 3 red, green, and blue features, whatever I've got. Pick one, just one to start with. Pick a cutoff for that, and then say, okay, if that number is greater, we'll go this way down the if-else branch, else we'll go the other way down the if-else branch. And then effectively recurse. Do that again, and then eventually, at the end of this process, every if-else branch has to end with, return prediction. So I'm not going to write it this way. I'm going to write it as if this, return 1. And each one of those ifs is going to have a corresponding else where I go off and I make some other decision maybe. I would probably rather just think of it like this, like a decision tree. So it's like, well, okay, I have a condition. My condition is always going to be some feature greater than less than a number that I make up. True, go this way, false, go that way. And for this data that I've been dragging around and I've used in a bunch of examples now, I can imagine this happening. Okay, I've only got 2 features in the world. So the thing that I'm going to call X, so I'm going to look at Y first. The thing I think about is Y. I would say, like, if Y is less than -6, return blue. Else, if X is like greater than 0, I'm green. If it's less than 0, I'm in category red. Like, that one I could actually write. So I'm going to phrase it that way. Like, I'm going to think of it that way in my head, but it's going to be drawn as a decision tree, because it's going to get way worse than 2 levels deep. But yeah, I can totally imagine this working, right? And again, like, I stared at that plot and I imagined -6 and 0 as those 2 cutoffs, but, well, let's not worry too much about it yet. So I can just do that. It's called a decision tree classifier. Training it is effectively like drawing this tree, or figuring out, okay, what feature am I going to look at? What cutoff am I going to look at? And then, true, false, off we go. I've said here my tree can be at most 2 steps deep, which is what I showed on the last slide. The default thing for a decision tree is basically to overfit, like, in the most horrendous way possible. So I really do need something here to limit. I'm going to go with that right now. But once I do that, well, training the training data, scoring, off we go, and we get, yeah, cool. Like, that's not bad. That's in line with the other scores we've seen for that data set. On the data over here, depth 2? Well, I don't know. Let's go for it. Or is it there? Okay. All right. Well, apparently on this data, depth equals 2 isn't very good, or something. Or maybe, I guess I don't know yet. Maybe decision tree classifier is just bad for this data. I suspect that I could do better than that. There we go. Okay, you know what? I'm going to stop there. I'm going to call that a win. I think it's a little worse than the other models on that data set, but hey, it'll do. So for this data set from the slides, again, where I said like 0 in the x-axis, -6 on the y-axis, what I would look at, the actual k-nearest neighbors thing did a little bit, like it's a little bit below 6, a little bit less than 0, but it's the same basic thing, right? This is the same effectively like 2 levels deep if else block. Yeah, I guess I'm pretty good. I'm pretty happy about that. It turns out you can just ask for this. It will, I don't know if anybody else has ever worked with GraphViz. It's a graph drawing tool. The only thing worse than GraphViz is every other way to draw a graph. But you just produce this, right? This is just, okay, so the y value less than -6.343. I don't know where that number came from, but hey, we got there. If it's true, we go this way and we predict category blue. Else we go this way and we predict either red or green. Okay, great. I don't know why, I guess I don't know why it chose Y first. I mean, I think it makes sense to do that, but I don't know how, I don't know what math went into that. And then we looked at these numbers, the -6.3, the -0.37. I don't know. They came from somewhere, but they're pretty good. Like it's a pretty good result. The other thing we're seeing here, I guess, just since I have this visualization up, it's in this data set, there's 375 training points that lead here. Okay, this is a start, so there's 375 training points. 123 of them go over here, and they're all blue. So all blue, 0. That way? I guess it's oriented that way, so green and red. So it's how does the rainbow get mapped to categories? I can never remember. And then, yeah, coming out here, about 2/3 of the data leads me in this direction. And then I have 122 data points here that I'm predicting red. They're mostly red, but there's a few green training points down this branch, and there's a few red training points down this branch, even though I'm predicting green. So the model knows that it's not perfect. Okay, can I use GraphViz in real time? No. But what I can do is just pause. I'm just going to pause. I'm going to set this up, and we'll see what I've been getting. Okay, what have I learned? That producing the GraphViz input file is not that hard. And then there's a bunch of magic that goes with running GraphViz and producing output. And in this case, what I got was this. And I don't know that this is hugely beautiful, but hey, it is. Well, okay. For whatever reason, I have 4 features here. So I have feature 0, 1, 2, and 3 as the default. Again, I look at feature 2, and if compared to 2.3, and I go to, okay, like, I don't know if this is illuminating to me. I guess I can see, like, I can see what I'm predicting in each case here, and then, how happy I am about it. Fine. Probably that's not the best visualization, at least in general. What's much more interesting, I think, are these hyperparameters that I now either have to or get to fill in, depending on your perspective. So yeah, over here, I went from, on the slides, I went from max depth 2 to max depth 4, and I got a little bit better score. And that's actually the same thing that happened in my notebook over here. Well, and now I start to think, well, if some is good, maybe more is better. Doubled it last time. And I start to get this business happening, right, where I am now overfitting, I think, right? Training score noticeably better than the validation score. I don't know, is there any other way I can convince myself of this? Not really. I guess I can still see it's the same categories that are hard, because they're always hard. Yep, boy, that's a lot. I guess I'm maybe not too surprised that I'm overfitting the data, right? So again, with 2 dimensions, I can give you this visualization and all is well. This seems pretty reasonable on this data on this slide, right? The depth equals 4. Yeah, like I'm giving it a little more freedom to make a little bit more like complex shape. I guess just inherently, it's maybe not immediately clear, but if I'm going to make this decision, I'm just going to look at one feature and I'm going to do a greater than less than comparison. Every boundary line is going to be like aligned with an axis, right? Like it's going to be a horizontal or vertical or higher dimensional analog of that word. Okay, but yeah, with depth 4, it gets to make, you know, a certain amount of stair step kind of thing in its output. Yeah, that seems pretty reasonable. That's a decision tree I got there. And I guess I don't know if you can see. It is broadly seeable. You know, like I see this kind of thing down here, that if I go down this branch, there was only 2 training points that get me here. Maybe I'm nervous about that. There's only 4 training points that get me here. Like, do I want to make a decision based on only 2 training points to lead me, you know, or I guess there were 6 at this moment. Those 6 training points are going to be red in one direction, green in the other direction. Maybe. I guess I'm okay here. Like my training score and validation score are not diverging. I have this visualization that I'm happy about. Maybe it's okay. Maybe I'm not sad. But the same thing, I expect the same thing to keep happening, right? The more freedom I give the model, the more it can follow the training data. Sometimes that's good until you overfit and it becomes bad. The default, by the way, for a decision tree is no limit. So effectively, the default thing for a decision tree is overfit completely as much as possible, which is a weird default, but I don't know. It's what you get. So yeah, this is just like create an absolutely perfect tree if you only look at the training data. Yep. Oh no, there it is. So I can certainly imagine like situations where this is a decent decision tree, but it is not for the data that I have on my notebook here. That is definitely overfitting. It's, you know, if I just looked at the score on its own, I don't know that I would realize that. That's a decent enough score. I don't know what, you know, I don't know how many things were there. It was like 25 or who knows, something like that. If I start dialing this back, I expect things to get a little more reasonable. And like, notice here, the training score is getting worse. That sounds bad, right? I am getting a worse training score as I go, but my validation score is actually going up because the model is better at predicting on data it's never seen before. Did I happen to just pick the right one? No. Okay, so it's somewhere, I guess if I'm only going to fiddle with the max depth, it's the best number is somewhere in this 4 or 5 range. I guess I'm happy with that. So and this is really true for a lot of the machine learning models. The amount of freedom I give the model means it can do more complex things. It also means it can overfit the training data. And I want to come up to the edge of one, but not get the other, right? It also means if I had more training data, it probably wouldn't happen. This is a way, by the way, every machine learning project that's ever been done in the history of machine learning has gone. The conclusion sentence is going to be, if only we had more data, it would have worked. Because more training data means you can have a more complex model without overfitting. So you just need more data. It's always the end of the story. So in this case, with max depth 15, Yeah, I'm overfitting, right? Because what we're doing here is the model has created this like tiny little peninsula of red just so it can capture one training point because we let it. Of course, the goal of the model is to match the training data as well as it can. But in this case, that was a mistake. And in fact, if you look at the decision tree, I said max depth equals 15. There's only about 8 or 9 levels in this tree, because as it gets to the bottom of every single one of these things, you know, there's like down here, there's 2 green data points there. Yeah, there's 2 green, category green points there and 1 category red. Okay, so it was able to draw a line between those two, but now there's only 2 data points that kind of support this leaf, or that this leaf is referring to, and 1 training point that gets you this leaf. Well, yeah, I'm suspicious about that, right? That even if I just tell that story, it feels like I'm overfitting. Over here, pardon me, I've got 21 green data points here and 1 red data point, and it split those apart. You know, was that the right thing to do? Probably not. That's probably overfitting. It's chasing around a single training point and making a decision based on it. That sucks. Now, all of those things, if you have some crazy photographic memory, the first node at the top of all of those decision trees was this one. Look at the y value and compare it to -6.343. That's interesting. At least there's some consistency to it. I guess it's not like if we go back to the story that I told about how do you make a decision tree, and it's pick a feature, pick a cutoff, and then, you know, pick the one that kind of is best, whatever best means, and then recurse. Well, I guess then I'm not surprised that they're all going to start this way, because all of them are allowed to go at least 1 level deep in their decision tree, so they all are going to make that same initial choice. I guess that makes sense. There obviously is some interesting math going on to building this decision tree, and I think what I've learned over the years is I don't personally care about it. So there's 2 fundamental things you can look at that will say, hey, like, should I look at this feature or that feature, and what cutoff would be good? And I guess they're kind of just coming from opposite sides of this decision. One of them is, how much can I learn by asking this question? The other one is, if I chop my data set in half in this spot, how pure, like how much, to what extent is there only 1 category on one side of the decision? That's a good thing to have. Or again, how much do I learn about what category I'm in? They're going to lead you to the same kind of thing. I'm just going to make a choice that is the most good. And frankly, like I've tried, you can play with these in the decision tree classifier, which I don't have open here. Yeah, it's criterion. Oh, you can also ask about log loss. My experience is this hyperparameter is not actually very interesting. I've never seen it really change what's happening. They are, yeah, again, it's a question of maximizing the purity, or like minimizing the mixing within the categories. God, it feels weird to say that sentence, but we're talking about data points here. The other one is, again, like, this is a Shannon entropy, and you want a lot of it. No, you want a little of it. But like I said, I feel like you should know those are there, right? Like, obviously there's some way this decision is being made, and it's, you know, it's the critical thing about how this tree is formed, but I don't think it matters. I think what really matters when you're looking at a decision tree is, how much freedom do you give the model to build a bigger tree? That is way more interesting, and it's a way better way to sort of, I don't know, focus your time when you're thinking about a decision tree classifier or other decision tree, like a decision tree regressor that we'll meet soon enough. So that hyperparameter, the only one I've seen, although obviously there's a bunch more I can use here. like there's a whole bunch of stuff I can say. The max depth, well, I guess I waved at the tree and said, look, depth 4, but maybe I should be explicit. It's, if I say that, what I'm saying is you're allowed to build a tree that has 4 of these comparisons, like greater than, less than comparisons, and then you must predict. By the time you get down to that level in the tree, you must pick a category and predict that category. I guess it's pretty, like, I think I don't have to think too hard about which one it is. Well, like here, there's a little thing here that you probably can't see. Well, I'm going to predict the category that is the most common, right? There's 5 categories and 81 data points are in that category and 0. Okay, I'm going to predict that category when I get to this leaf. That much is easy. But how do we decide when and how to stop? Other things that I think, like I do think these hyperparameters are at least named well. How about that? Max depth, yeah. How deep can the tree be? Min sample split. Well, if I'm going to have a split, if I'm going to ask the greater than, less than question instead of just making a prediction as I go down the tree, how many training points do I need to do that? So if I say min sample split equals 30, well, on this node, I'm allowed to split because there's a number greater than 30 there. But like somewhere else here, samples equals 5. There's only 5 training points that would lead me to this point in the tree. That number is less than 30, so I would have to make a prediction here if I'd given this. Well, let's try it. What if I say that instead? I'm putting a different limit on the tree. That's, yeah, a little overfitty. I probably want to dial it back. So I don't want to make decisions with this few samples. That is overfitting. So therefore I want that number to be bigger. Sure. Why don't we try that? Has that updated? I think that's updated. All right. It's a smaller tree. It's a better score. Again, I think the visualization is cool. I don't think it's really so useful. You know, it is interesting to see what's going on here that, you know, like I can see way down here at the bottom. Like I came to this point where there were 51 samples here. There's only 2 of them in this other category. And I actually still mispredicted because, you know, it had to make a decision based on what it was, and wherever these points were arranged, this is the best it could do. Yeah, maybe I do want to limit that a little more. I don't know. Again, for this data, I think I'm going to probably be pretty happy. What's the other? Oh, min samples a leaf. This is how many training points have to lead to a leaf in that tree, you know, a decision. So I have to have it, well, at least this is expressing, I have to have at least 10 training points that lead to a decision. If I don't, then I'm not allowed, I have to kind of back up in my tree building. I'm not allowed to split in that direction. Both of those will limit things. I can combine them. Like I can say, you can go until there's only 4 data points on a leaf, but at most 6 levels deep. In some ways, this makes me feel good, because now I have some dials that I get to turn as a data scientist and make better predictions. Gaussian naive Bayes, I just had to sort of accept, you know, whatever probability distributions it calculated, and off we go. One of the things that is going to be a problem here, and it just is a problem for decision trees, is like giving a model enough freedom to do the thing and overfitting. They almost seem to overlap. Like as I try to make things, if I give the model more and more freedom, I start to see overfitting happening before the model is complex enough to really do its job, which is unsatisfying. If only there was some way to deal with that. Huh, guess I better flip slides. This could be true for other models. Like this, I'm talking about trees here, but this trade-off can be hard because, again, like I want a really, really complex model because my world is complex and I want to make complicated decisions, but I have a finite amount of training data, and it's very easy to overfit as I let the model complexity kind of drift upwards as I'm playing with hyperparameters. And I end up with both of the, like, it's really unsatisfying, right? When like my models are not complex enough, but I'm overfitting. Ugh. But one thing I will point out, I'm doing better than chance, right? If I have 5 categories here, they're equally weighted. So like if I see any number more than 0.2 here, at least I should be a little happy, right? Like if I really constrain things, just gonna go max depth. If I really constrain things, yeah. Okay, this score is lower than the other scores I've seen, but it's not worthless. Like if I had just, like if there was a like pick random category classifier, I would expect to see 0.2 here. I'm doing better than random chance. Hooray. It turns out you can get somewhere with that. If you have a bunch of classifiers that all do okay, they're making decisions that are, you know, pretty good, as best as you can get them, and they're a little different, well, then they would make different decisions sometimes, right? Like sometimes they would go one way or another. Why don't we just put them together and let them vote? I'm sure there's a lesson about democracy in here, but I can't, I don't know how to land that joke. So it just turns out that you get often, sometimes, if you have a bunch of classifiers that are pretty good and you just let them vote, you get a decent enough result. So you can do this explicitly. There's a thing called voting classifier that literally just takes a list of classifiers and it does the thing and lets them vote. I don't think you need to do that. Like this seems like a bit of a pain. I'm sure I can make up a story where it's worthwhile and it's worth it, but I'm not even going to bother. One kind of ensemble that is really useful, because again, decision trees are easy to make, they're easy to run, they're fast, all of these things are great. But again, they tend to be either overfitting or too simple. But if we make our decision trees just a little bit too simple and not overfit, then we can have a bunch of them. Well, we better make sure they're different. Because of course, if I have 100 identical decision trees and I let them vote, that's a really boring vote. But if I can have trees, like I somehow randomize the construction enough that they end up different, even if that makes each individual one a little bit worse, put them together, let them vote, call it a random forest because a bunch of trees are a forest. So the construction, like I said, we need some randomness in here. Typically, it will be like a lower max depth or more constraint on the min samples leaf, min sample split. Somehow constrain the classifier. Probably a little bit more than I would have a few slides ago. And then somehow make each tree a little bit random. One way to make each tree a little bit different is to use the same like tree building algorithm, but hand it a slightly different data set. Just randomly sample half of the data, train a tree. Randomly sample half of the data, train another tree. Well, randomness being randomness, maybe that would work out. I need more links in my slides. And that's exactly what the random forest classifier is going to do. I've got all the things I can do with a decision tree. So those things were the same, except it's how do I want to randomize things gets added in there. So the other option, and it's hard to make this land when I only have 2 features in my example that I have in the slides. But if I have something like the breast cancer data that has 30 features, well, for each node, like for each node I'm drawing in this tree, just randomly choose half of them or whatever fraction, and just say, okay, when whatever gets drawn in this node in this decision tree has to be one of those features. You're not allowed to look at any of the other ones for this thing. We can look at them maybe in the next layer, which, well, if it's a random subset and a random subset, well, the construction is going to be a little bit random. Each tree should be a little bit different. Make a bunch of these, let them vote. Like I said, the parameters that are the hyperparameters that I get to give when I'm creating a random forest classifier, which is an ensemble of trees, are the same kinds of things I can say for a decision tree, plus how many trees are in the forest, plus some things that I don't think I'm going to play with that are like, again, how do we introduce a randomness into the story? I think the default's probably cool. And like in the sample and sample data on the slides, I do a lot better. Let's see how I do here. I'm gonna need an import. I'm glad Pass Me at least put the import statements on the slides. So is that better? Well, not better than we've seen, but we also have a different data set, right? Like this data, it has more data points, it has more features. I can probably get away with a more, a little more freedom in the model. And yep, and even still, like I'm definitely not overfitting, right? That's actually a bigger score. So I can probably, I don't know, like at some point, I'm presumably going to start overfitting here. Training score actually went down. That's a surprise. What if I just remove that limit altogether and let the tree be deep? Finally, I'm overfitting. So again, I want to put a few more constraints on this so I don't overfit my training data. So maybe this limit, the score went down. So maybe this number is too big. I'm not giving the tree enough freedom to understand the data. It was a little bit better when I had that. I'm going to call that the winner and move on. There is, by the way, randomness in this, right? So maybe I was just chasing around randomness because it is a random forest. Every time it gets constructed, it's going to be a little bit different. So I expect everything to just be a little different. Hopefully not too different, but a little bit. That'll happen. Okay, again, this one where I'm drawing the decision boundaries in my two-dimensional world. Yeah, that I get behind that. Again, the fundamental question I'm asking myself as I'm evaluating these is, do I trust this model to make predictions? So, I'm getting 92% on my validation data here. It doesn't look, if I get to draw a visualization like this, it looks reasonable. If I look at the other things that are going on here, all right, I can't draw the one tree because there's not one tree. I guess I'm reasonably happy, based on, everything I can see, but that the validation score is going to be the first thing I look at, but maybe not the last. I think I trust this model. I think I'm happy with it. Again, both in the slides and in the notebook. It turns out you can, if you poke around deep enough in the random forest, you can get a list of all the trees and then you can draw them. So this is what I got for those ones. And you can see like one of these trees makes the same y less than -6,343. This one makes a different y comparison. This one starts with an x comparison because they were limited that way. So this is like, apparently the thing you do is take the square root of the number of features by default, and that's randomly choose that many features for each node you're drawing. I don't know. I don't know why that's the default. I have a vague sense that it might have changed at some point, but anyway. Oh yeah, there was a change. Anyway. But point being, I get slightly different trees. And this is 3 out of 100. Yeah. The first 3 or whichever ones I chose. Okay, each one of these is going to make a little bit different decision. If I picture only these three trees, well, again, I have some point, and this one predicts green, and this one predicts red, and this one predicts red. So I vote, and we choose red for that point as a prediction of the forest. It seems to work. Each individual tree is kind of stupid. That's okay. We're going to put them together. It's going to work out if we kind of tune everything correctly and just so. Oh, right. I kind of implied this was going to be the case and didn't say it. We are kind of dealing with overfitting here because one of the things that happens is that bootstrapping sample, if I train one of these trees with a subset of the data, well, it can't overfit the rest of the data because it never even saw it during the training process. So these like two interlocking arcs data sets, this is not very helpful. Let's go to my next slide. This kind of data where we've got these two arcs, well, it's perfect. You know, both the training and validation scores are 1. The decision boundary looks weird, and the decision boundary looks weird because there's no training data in the middle. So there's nothing to constrain the model in any way. So there's just kind of this randomness happening. It looks the same as overfitting. This is actually under training. Like this is just, there is nothing happening there. There's no way, well, based on, you know, the story we're telling here, there's nothing that is done to in any way tell the model what to do in this desert in the middle with no data points. So you kind of get some weirdness happening. One of two things is now true. Either data points in here never exist and I don't see them, I will never see them, and I don't care about it, or my training data doesn't represent the things that might happen and I need some training data to sort that out. Like, again, with fake data, neither one is really true. It's just fake data. But, well, if I don't have training data that is an example of whatever is going on here, if that might happen, my model is going to be really bad at that. I know this is, well, it's off topic and it isn't. That's probably it. It turns out if you ask any of the AI image generators to draw a full glass of wine, no, seriously, full, fill to the brim, not a drop more wine can go in this, no, seriously, full, it doesn't matter what you say, it can't drop because there's no training data for glasses of wine that are full to the brim. So yeah, they don't do that. Interesting. Anyway, I don't actually know if this is the original thing I saw or not. It's certainly the same effect. It was, yeah, like with the prompts getting increasingly desperate was the story. It's like, oh my God, please, that wine, there's still room for more wine in that glass, or one that's fuller. You can't do that because there's no training data. And obviously an AI image generator and this random forest on my slide are a very different tool. But if there's no training data, there's nothing to train that outcome. So who knows what happens. Anyway. Which, by the way, is another, like, all these generative AI tools, like, they're kind of inherently can't generate something new. That's just not what they do. Anyway, what was I talking about? Okay, ensembles and random forest. Okay, so random forest is great, right? And I tell this story where it's like somehow randomize the world a little bit and create a decision tree, and then do it differently. Like, just let the randomness fall in a little bit different way. Create a decision tree, different kind of randomness, different decision tree. Okay, great, that's fine. All of those were independent decisions, right? I just sort of said, when you're creating a thing, randomize the data set, randomize the features on each thing, whatever it is. But maybe we can do better. Maybe what we can do is say, okay, you know what? I'm going to take my training data each training point gets a score of 1. We'll start there. And then I'm going to look at the score, the weight on each training point, and I'm going to use it maybe a little bit more. Like the ones that are hard, the ones that I have predicted wrong in the past, I will increase their weights, and then I will kind of concentrate on them as I train my next tree. And that idea is boosting. And the way it's going to work out is, again, like start with everybody has a weight of 1 or whatever your constant is, and then create one of the trees in the forest and see how you do. Some of the training points are going to be right, some of them are going to be wrong. You hope that a lot of them are correct. So of the training points that are incorrect on that first decision tree that I created, move their weights up a little bit, move the other weights down a little bit. Okay, and then repeat. The next time I train a decision tree, I weight the score a little bit. So if you get one of the high weighted training points wrong, that's worse than getting one of the low weighted training points wrong, or whatever is going on here. So you're sort of biasing the next decision tree to look more carefully at the higher weight training points, because those ones are the hard ones. The easy ones, don't worry about it. We're going to get the easy ones right. Focus more on the hard ones. Those are harder. Let's put our effort there. Basically, concentrate on the hard part of the problem. So these things, like these two boosted tree classifiers, I think they're both boosted trees. Just again, empirically, like I have no theorem here, obviously, right? It seems like for sort of machine learning problems that are on the data science scale, like I'm not talking about text generation and image generation or whatever here, boosted trees seem to do pretty good. If it's just like, look, I have this data set, I want to predict this thing because I would rather not measure it, or I'd rather not pay to have it measured, or I want to predict what it will be in the future, or whatever, a boosted tree seems to work pretty well. And graded boosted classifier here. This is the best score we've seen on the breast cancer data, which is what I'm working with on this slide. I can tell you right now, this demo is going to fall flat, because what's going on here is like this fake data I have in my Jupyter notebook is just not interesting enough. There's just not enough cool things going on in that data set. Geez, it's as good a score as I've seen on this data. I probably could fiddle with it, right? I could probably do a little bit better, considering I just randomly copied some parameters off the slides. But this just seems to work pretty well. It just seems to be people's experience with it. That's a pretty good score for this, like, not easy problem. It's a real problem with real implications in the world, and we can do pretty well. Hooray. All right, what are we at here? Okay. So as we start, I'm sort of alternating here, I guess, right? I'm alternating between like building up another machine learning tool that can make predictions and techniques that you can use around them. Here's one. It's how many features do you have? Like effectively, how wide is your data frame? How many columns does it have? Kind of -1. Presumably one of them is the target and the rest are features. Okay, the breast cancer data has 30 features. That again, have real meaning. And I probably should know about them, but I don't. The weather data, 60. It's also not a huge number. I understand weather data more, right? I understand what it means to have a maximum temperature and whatever. But it's easy to have a lot. And like that handwritten digit recognition example where it was these comically small bitmap images of 8 by 8 pixels, well, that's still 64 features, because 8 times 8 is 64. That's still the biggest number on the slide I've got, and that's comically small as images go. Here's didn't I fix this? I fixed the link and didn't reload my slides. Great. This labeled faces in the wild. This is, well, it's from a very specific, I'll just show you the example. It's another, I guess, by the way, it's another thing that like scikit-learn can just create this data set, download it for you. You know, you can kind of tell like in which year this data set was created. It's these pictures of people who are famous, were famous, are monsters, except Koizumi. As far as I know, he's cool. But okay, so these are images that are also comically small, right? These are black and white images that are tiny in the size of modern images. There's a pretty modest data set here. So I've said only keep people who have at least 60 images in the data set. So there's probably some other people here, but these 8 politicians from the early 2000s, I guess. Late 90s? Anyway. Okay, and the problem is, I guess, the person is the category and each pixel is a feature. So given this image, is there something about this image that you can use to produce George W. Bush as the category that this is in? And I'm always surprised, like, I'm picking support vector machine here that I know I didn't talk about yet. It doesn't matter, it's fine. Like, I don't think not knowing about support vector machines is gonna be a detriment to you, but I'm gonna use it here because I wanna talk about how much computation is used by these tools, and this one's a little expensive. But hey, if I just do that, if I just shovel this data into this randomly chosen thing, I didn't, you know, it's not like whatever hyperparameters are here, it's not like I thought very carefully about them. And I get 80%. That's not bad. Because remember, I have 8 categories, so anything greater than an 8th is a win. I can predict 80% correct which early aughts politician is this tiny image represents. Okay. But it takes real time. I can do worse with these other tools. They're much faster, but it's worse, right? One thing I do know about support vector machine is the running time is, I think, linear in the number of features. So if I say, okay, linear in the number of features, and I have 12,000 features, I think I am sad. Well, if I'm sad about 8 seconds, then that's maybe why. So I think I'm going to have to stop there because we end. I am, as I said, I'm not going to have a lecture next week, I believe, and I'll send an email about that, though, to be sure. I don't know. See you in the lab, I suppose. Bye.